Hello guys, my name is Desmond and I welcome you to my lesson for today. Ladies and gentlemen, I hope you fully understood on my previous lesson where I was explaining all of that. For objects, ladies and gentlemen, moving on a horizontal plane. Okay, so now I just decided to leave all of that while I do this lesson for objects being projected vertically upwards or downwards. Okay, so now we focus on vertical movement. Okay, so ladies and gentlemen, I'll just be going through the same process where I sketch the graph of delta y, and you see the difference, ladies and gentlemen. Delta y versus delta t, v versus t, acceleration versus time. Okay, so remember guys, in this case, because we're dealing with objects moving up and down, that's why instead of a over there, let's use a g. Very much important, ladies and gentlemen. I hope you fully understand that part over there. Okay, so guys, let's start with the first one, and then from there we'll just nicely come up with all other related scenarios. Okay, so the first one, ladies and gentlemen, let's focus on an object dropped from a height. Listen to this very carefully, ladies and gentlemen. An object dropped from a height. Okay, so someone might be standing on the edge of a cliff or from a building. Let's say there is our friend over there, ladies and gentlemen. So what happens is he's got a stone. Let's say it's a stone at the top of that mountain or a cliff or whatever it could be. Okay, so ladies and gentlemen, what happens in this case is that an object is being dropped from a height. Let me just write it down. Dropped from a height. So that means this is the first scenario, ladies and gentlemen. Write that down as part of your notes to say the first scenario is where an object is dropped from a height. Okay, obviously, ladies and gentlemen, if it's dropped, it's going to then fall until it hits the ground. In this case, ladies and gentlemen, as soon as it hits the ground, it doesn't bounce. It just falls from there, hit the ground, and then it remains attached to the ground. Okay, so now let's try to draw the graph of delta y versus time. Okay, so ladies and gentlemen, in this case, you've got a graph of delta y in meters. Remember, at all times you've got change in t in seconds. Okay, so ladies and gentlemen, in this case, remember guys, in this case you've got an object which was at a certain height. Okay, so obviously this is the height that we're talking about. Remember guys, in this case delta y is a vector quantity. I hope this won't confuse you guys. A vector quantity, it's a quantity that has a value and a direction, and then we also have a scalar quantity which has just a value. So for example, time, it's a scalar quantity. It can be just 2 seconds. Okay, but a velocity, it can be a v, which is 20 meters per second to the right. Okay, so this is the value and the direction. Okay, so this is just the value. That's why we say velocity, it's a vector quantity because it has a value and a direction. This is a scalar quantity because it has a value. Okay, so ladies and gentlemen, delta y is a vector quantity, which means it has both the value and the direction. In this case, what is the direction, ladies and gentlemen? You can see this object is covering a distance but downwards, okay, on its way down. So for example, in the upcoming examples, we'll be having a situation where an object is being thrown vertically upwards and it comes down. So in that case, ladies and gentlemen, obviously as it goes up, it covers a distance in a certain direction. As it comes down, it covers a certain distance in a different direction. Okay, so that's why it's very, very much important, ladies and gentlemen, to indicate that just to firstly extend that line. Okay, to say obviously from there at the top, that's where the distance is 0. Okay, so obviously as time goes on, ladies and gentlemen, as time goes on, it covers that distance. Okay, but remember guys, as this object goes down, it moves from a position where its velocity is equals to 0. As it goes down, its velocity is increasing. Okay, it's going up. Okay, for the fact that as it goes down, its velocity, it's not just constant but increasing. That's why the shape of the graph is like that. Okay, so it's more like, otherwise if this was just moving at a constant speed, we're just going to have maybe a straight line. But for the fact that this is increasing its speed, so that means as time goes on, it covers a long distance within a short space of time. Okay, I hope you fully understand that part from the previous lesson. Okay, so ladies and gentlemen, let's now sketch the second graph of velocity in meters per second versus delta t in seconds. Okay, so ladies and gentlemen, if you fully want to understand this part, remember, same scenario, but this is velocity versus time graph. Okay, so guys, because this object is being drawn from the top, it's best to just extend this line. Remember guys, on this side is the positive side, on this side is the negative side. So this is in a situation where we say up represents positive and then down represents negative. Okay, so that means when we draw on this side of the Cartesian plane, it means that object is going downwards. If it was an object thrown vertically upwards, maybe we're going to draw on that side. Okay, do not be confused, ladies and gentlemen. Obviously, as time goes on, what happens to its velocity? It's increasing. That's why we've got a graph in that direction. Okay, so ladies and gentlemen, it's not a curving shape. The curving shape applies to a situation where we normally sketch the distance versus time graph. Even if you can have a look over there on the previous lesson, you will realize that we've got two cases there where we've got a curving shape, and it only occurs in a situation where we've got increasing speed or increasing velocity, okay, or increasing acceleration. So not necessarily increasing acceleration, I mean in increasing speed or decreasing speed. That's when you've got a shape which is a curving. But in this case, velocity versus time is just a straight line but at an angle. Okay, so ladies and gentlemen, I think now we can move to the last type of a graph, which is that one of acceleration versus time. Okay, so ladies and gentlemen, it's g, let's just say g in meters per second squared. Let me see, ladies and gentlemen, I'm just trying to think on this one. Okay, let's say delta t in seconds. Okay, so remember guys, that g, which is constant, okay, obviously because this object it's been dropped from a certain height, so the acceleration, which is just constant, in this case we just have a straight line but on the negative side of that Cartesian plane, because obviously the acceleration it's being applied downwards, and at all times we know that the gravitational acceleration or force of gravity is exerting everything towards the ground. Okay, so we'll just see as we continue, ladies and gentlemen, if we've got the difference in terms of how we represent the acceleration versus time graph. Remember, in this case is gravitational acceleration. That's why I've got G over there. It's always constant and it's always exerting in the same direction. Okay, so ladies and gentlemen, can we now focus on an object? Remember guys, this was an object which was dropped. The key word here is that this was dropped. Okay, very, very much important, ladies and gentlemen. Let's now focus on an object which is being thrown thrown downwards from a height. Okay, you can just write down as your note, thrown, HROWN, thrown down from a height. Okay, obviously, ladies and gentlemen, the same friend of ours standing over there, but in this case they throw that object. Okay, it will obviously go down, okay, until it hits the ground. Okay, very, very much important, ladies and gentlemen. So now let's sketch our first graph. At all times, never get tired of writing the correct thing, ladies and gentlemen. Delta y in meters, that in seconds. Okay, so remember guys, in this case we're also focusing on object which is still going down, but the difference in this way, in this case, is that it's being thrown. It's not being released or dropped. Okay, it's being thrown. I hope you notice the difference over there. So this is thrown downwards, so that's why it might be necessary for us to extend so that we know we've got the positive side and the negative side of the graph. Okay, very, very much important, ladies and gentlemen. So now let's try to draw that type of a graph. Obviously, ladies and gentlemen, the same happens. At that point there, the distance is still 0. As time goes on, it covers that distance. As time goes on, it covers that distance. And because as it goes down, its velocity increase, it means after some time it will still be covering shorter distance within short space of time. Okay, very, very much important, ladies and gentlemen. So this is how the graph looks like for an object which is being thrown vertically downwards. Okay, so again we still have that graph of velocity in meters per second versus delta t in seconds. Okay, so ladies and gentlemen, it's very, very much important it's very, very much important that you fully understand. Remember, we're still dealing with that situation, so it might be necessary for us to just extend it a bit. Okay, obviously guys, at that point there, its velocity, it's obviously 0, and they throw it down, so as time goes on, its velocity increase. Okay, so ladies and gentlemen, it's almost the same as the previous type of an object. So ladies and gentlemen, let's now draw our last type of graph. G in meters per square second, delta t in seconds. Obviously, ladies and gentlemen, same thing. Okay, on the negative side of the graph, and the value remains the same, which is 9.8. Okay, only for objects moving up and down. Ladies and gentlemen, I think we can now move to the next situation. Okay, let's have a look at the object which is thrown up from a certain height. Okay, so guys, remember that the best advice that I can give you is that just watch it for the first time, by just seeing what I'll be doing. Watch it for the second time, trying to apply your understanding. Watch it for the last time where you write down your notes. From there, you can go through your notes to make sure that you understand, such that you will still understand the same notes in 10 years time to come. Okay, so ladies and gentlemen, we've got our friend which is at the top of a building. Okay, but in this case, our friend, what they do is to throw this object from from a height, from a certain height. Okay, so remember, this is it's a flat, ladies and gentlemen. This is the Sicalo chord. Okay, so ladies and gentlemen, they throw it up. Obviously it's going to go up. Okay, from there it's going to go down and hit the ground. Okay, very, very much important, ladies and gentlemen. So remember, this is our reference point over there where our friend is standing. Okay, they throw it up. As it goes up, obviously its velocity decreases until it reaches its maximum height. Then it goes down, and then it passes that level over there where it was thrown, and then from there it continues going down until it hits the ground. Very, very much important, ladies and gentlemen. So now let's try to do some drawings. Okay, so ladies and gentlemen, obviously our first graph is that of delta y in meters versus that of delta t in seconds. Okay, so here you need to be very, very careful, ladies and gentlemen. Remember, initially the distance is 0 at that point over there where it's being thrown vertically upwards. Okay, so ladies and gentlemen, as it goes up, it covers a positive it covers a positive height. Can you see, ladies and gentlemen? So that means this is the reference point over there, which is that point over there. Okay, so obviously it's being thrown and then it covers the positive side. Can you see, ladies and gentlemen? It goes up. That's why our graph starts from there and then it goes up until it reaches its maximum height, and that object now is changing direction. So that's why our graph will go like that. Why? Because it's now covering the distance but in the opposite direction. Okay, so ladies and gentlemen, when it gets to that point over there, it's that point. So that means if it takes 4 seconds to reach its maximum height, it will take 4 seconds to come down to that same level from where it was thrown vertically upwards. Okay, so that's why you've got that which is symmetrical to that part. Okay, so if you cut that into half, you get the same time. Okay, so it doesn't end there, ladies and gentlemen. It continues with its journey going down. Okay, and you can see it travels longer distance when compared to when it was going up. So that's why this line, we extend it and it's a bit longer than that one. Okay, it's because from there to there is just a smaller distance, and then from there up until it hits the ground, it's a bit longer. Okay, so ladies and gentlemen, that's why this graph, it looks like that. So now let's draw another graph. Okay, so ladies and gentlemen, this is that one of delta t in seconds versus velocity in meters per second. Okay, very, very much important, ladies and gentlemen. So obviously, guys, this object, what happens is that it's been thrown vertically upwards from a certain height, then it reaches its maximum height, and then from there it comes down. Okay, so ladies and gentlemen, in this case, this is how you represent this graph. So that means it's been thrown vertically upwards. Okay, it's been thrown vertically upwards, and as it goes up, its velocity decreases, ladies and gentlemen. Its velocity decreases. Okay, so you need to be very, very careful of this one, ladies and gentlemen. It starts at a certain speed. That's why that dot is there and not there, because there it's 0 if we draw, we make a point there, it means it starts at a certain speed or velocity. So it goes up, and as it goes up, ladies and gentlemen, its velocity decreases. That's why this graph, instead of going that direction, it goes downwards. Why? Because the speed is decreasing until it's 0. Okay, this is that point over there. So obviously from that maximum height, it goes down. Okay, what happens to its speed? It increases, but in the opposite direction. That's why we extend that line. Okay, we extend it up to somewhere there. Okay, so remember, this is just the negative side, this is just the positive side, which refers to the direction. Okay, but in terms of the values, the numbers are increasing: 10, 20, 30, 40, 50, 60, whatever. So do not say it's negative 30, therefore it's less than positive 30. In physical sciences, especially on the graphs, the negative sign doesn't mean the number is small, but it tells more about the direction. Okay, so I stopped it there, ladies and gentlemen, which means that time from there to there, it should be the same time as from there to there. So it's more like for this object to go up to that point and also to come down to that point, it takes the same time. Okay, so remember guys, as soon as it gets to that point, it continues with its journey. That's why this line is now being extended and it's now a bit longer. Okay, it's a bit longer, unlike if, let's say, our friend was standing on the ground and that object just goes up and then it hits the ground. Okay, but in this case, it's been thrown vertically from a certain height. That's why it will go up and then it comes back to that same level and then it continues with its journey. Okay, so ladies and gentlemen, I hope you fully understand this part. Okay, so now let's move to that graph which remains the same at all times, ladies and gentlemen, which is that one of G meters per square second. We obviously know it's 9.8. It remains the same. Okay, very, very much important, ladies and gentlemen. This is for a situation where we're dealing with objects moving up and down. Okay, very, very much important, ladies and gentlemen. So now, how about we focus on an object which is, being thrown up and being caught. Okay, very, very much important, ladies and gentlemen. Thrown vertically upwards and being caught. So in this case, the difference is that it's not being thrown from a certain height. Okay, you will see maybe when I draw the diagram. So let's say it's thrown and caught. So that means, let's say we've got our friend over there standing on the ground. They've got an object there. They throw it, it goes up, and then they catch it. I hope you fully understand that part, ladies and gentlemen. So you throw it up and then you catch it. Okay, so guys, our very first graph, in this case, let's just try to draw it. Obviously it's delta t in seconds, is delta y in meters. Okay, so obviously, as you can see, ladies and gentlemen, it covers a positive direction, and then it covers a positive distance on its way up, on its way down. It covers the same but in the opposite direction. And remember, the reason why we say thrown and being caught is because it doesn't go beyond, just like when it's thrown from a height. Okay, so remember, this is the hand. Okay, this is the ground, so it's been thrown from the hand and then caught. That's why it remains at that level. So ladies and gentlemen, initially at that point it was at height 0. As it goes up, it gains height up until it reaches its maximum height over there, and then now it comes down, it covers the same height, and remember, it takes the same time. So that means if you cut that into half, it takes the same time for it to go up and down. Okay, so now that was easy, ladies and gentlemen. Let's now focus on the second graph, delta t in seconds, delta y in meters. Okay, so remember guys, this is velocity, not delta t, delta y, because we've covered it there. So now in terms of the velocity versus time, obviously as it goes up, it initially starts at a certain speed, okay, and then as it goes up, its velocity decreases, okay, until it's 0, which is that point there, and then from there it changes direction, and then it takes the same time. So that means that line is equals to that line. Okay, so if it took 3 seconds for it to reach that maximum height, it will still take 3 seconds for it to get to the hand where it's been caught. Okay, very, very much important, ladies and gentlemen. And now we get to that same graph of gravitational acceleration meters per second squared. Okay, it's 9.8. You just draw it like that. Ladies and gentlemen, never get tired of writing the unit. Okay, it's very, very much important. If you say velocity, also write to say in meters per second. If it's the time, also write to say it's in seconds. Ladies and gentlemen, let's now focus on a situation where you've got a flat over there and then we've got our friend, and then they throw an object vertically up, and then obviously it lands at the top of that building. Okay, so in this case, ladies and gentlemen, let's also try to draw some graphs. Okay, obviously at all times we start with delta t time in seconds and delta y in meters. Okay, so ladies and gentlemen, obviously this object is covering a distance in the opposite direction, and then from there it also covers in the negative direction. Okay, but in this case it goes up, and on its way down it doesn't go beyond a point where it was thrown vertically upwards. So this is how the distance will look like. It covers a certain distance, and then from there it stops at a certain height. Okay, so that's why the graph looks like that. Is because it covers a certain height which is increasing. This is the height which is increasing. It is increasing. It reaches a maximum height, which is that point, and then it starts to cover another height, but in the opposite direction. That's why that graph is now going down, but up to a certain height. Okay, so ladies and gentlemen, let's now move to the other graph of delta t, time in seconds, and then v in meters per second. Okay, so ladies and gentlemen, what happens in this case? Obviously, as it goes up, okay, as it goes up, its velocity decreases. So it starts from a certain velocity. This is the initial velocity. They throw it up at a higher speed, but as it goes up, its velocity decreases until it's 0, and then it starts to come down. Okay, and as it comes down, that means it starts from 0, and then it starts to increase as it comes down. Okay, so ladies and gentlemen, this is how you draw the graph. As time goes on, its velocity decreases as it goes up until it's 0, which is that point over there. Okay, then now you draw a short line, ladies and gentlemen. Just extend by a short line, because remember, this is the positive side, this is the negative side. It simply means on the positive side, that's when it goes up, its velocity increases until it's 0, and then from there, at this point, now it comes down. So that's that portion over there. It comes down, but it's a shorter line, because as it comes down, it doesn't reach to that same level. Okay, so it's as simple as that, ladies and gentlemen. From there, what we do is just to draw that last one, which is just the same, ladies and gentlemen, which is the meters per second squared. Okay, and point A to just draw a straight line. Very, very much important, ladies and gentlemen. Never get tired of writing the SI unit. Okay, so guys, let's now focus on another situation. Let's say maybe our friend standing on a building, okay, so there's a balcony there. So now what happens is that our friend throws an object up, it goes up and then it comes down, it hits the balcony. What happens, ladies and gentlemen, it will hit the balcony and then go up a bit, and then from there it hits the ground. Okay, so ladies and gentlemen, how do we represent this type of a situation on a graph? Okay, it's going to be something a little bit funny, I assume. So obviously we start with delta y, which is in meters, delta t, which is in seconds. Okay, so ladies and gentlemen, let's just try to have a look. You started at that point to say the height. This is the reference point, ladies and gentlemen, in terms of the height. Okay, so obviously that's where the height is 0 there, and then that height increases, and then it starts to obviously get to its maximum height there, then it comes down. Okay, very, very much important, ladies and gentlemen, it comes down. So that point, it's along that same line where it was thrown vertically upwards. Remember guys, the heading of this situation, you can just say thrown, let's say thrown up from height and bounces. Okay, it's thrown from a certain height, it hits, and then it bounces. Okay, but it's different from when it's been thrown up, then it hits the ground, and then it bounces from the ground. In this case, it hits the balcony and then it goes up, then this is the bouncing that we're referring to. So that point over there, ladies and gentlemen, that's where it's along the same line. But remember, it continues, guys. It continues, let me just say, it continues up to that point over there where it hits where it hits the balcony. As soon as it hits the balcony, ladies and gentlemen, it covers another height, but in the opposite direction. That's when it goes up, and then that point, which is the turning point, is that point over there, and then from there it goes down. Okay, so it's more like we're just redrawing the path of this thing. Okay, very, very much important, ladies and gentlemen. So now let's draw delta t versus velocity in meters per second. This one is in seconds. Okay, very, very much important, ladies and gentlemen. So now remember guys, it's been thrown vertically upwards, meaning it has a certain speed and it reaches a maximum height. So this is how you draw it. From a certain height, it reaches its maximum height. That point there, this is where its velocity is 0. And then from there, it comes back in the opposite direction. Then we just extend the line, a straight line. It has to be a straight line, guys. You extend the line up to that point over there. So when it gets to that same level, it continues going down. So we also extend the line. Okay, very, very much important, ladies and gentlemen. So obviously now that we extend the line, what we normally do to represent the speed, obviously remember, as soon as it hits that point, it obviously goes up again. Okay, so that means it's gaining a speed, but in the upward direction. Okay, so that is why, ladies and gentlemen, we will start along that same time. along that same time, we start to draw again that type of a line. Okay, so that type of a line, it simply means at the same time there, as it hits the ground, it now changes a direction. Okay, it's covering speed in the upwards direction, and as it goes up, its velocity decrease. That's why we had to start that graph somewhere on this positive side of the graph, so that its velocity decreases as it goes down. So the similarities here, ladies and gentlemen, is that you've got two situations. It's like it's being thrown, someone catches it, and then they do the same. Can you see, ladies and gentlemen? So remember, as it goes up, its velocity gets to a point where it's 0, which is that point there, and then it comes down. We just extend the line, a straight line, same explanation that we went through there. Extend the line, a straight line, same from there to there, from there to there, it has to be the same, which is that point from there to there, and then from there to that same level. Then because it then continues, then we extend that line. Okay, ladies and gentlemen, I hope you understand that part. Okay, so now guys, this one you can easily explain to me. I hope I won't have to spend much of our time on this one. It just remains the same throughout. Okay, ladies and gentlemen, very, very much important that you fully understand what I've been explaining to you guys. So guys, thanks very, very much for joining. I hope you enjoyed this lesson, and I hope to see you on my upcoming lessons. So the next lesson that we'll be doing is just to do practice questions, where we just pick any type of a problem that we solve. So that's why I'm going to show you how you pick a formula to solve for the unknown. And then from there, ladies and gentlemen, I would encourage you to check out one of my live lessons where I was solving exam question papers. Okay, then we'll be completely done with this chapter of vertical projectile motion, ladies and gentlemen, which will form part of your exam, I think, for term 1 for matriculants. And ladies and gentlemen, please try to watch these lessons as many times as possible, so that towards the end of the year you will still remember everything. I can tell you, ladies and gentlemen, I can promise you, you will never go wrong. Ladies and gentlemen, a day without learning something new, it's a day wasted. I hope at this point in time you all understand that a day without learning something new, it's a day wasted. So guys, please do make sure that you practice a lot more. And again, in case if you need some study material, you can just drop me a WhatsApp number on this a WhatsApp text on this number, ladies and gentlemen. It's let me just, I think I can just remove this part and write down the number where you can just drop me a WhatsApp. It's 074-866-3830. So you can, at any time, at any day, you can just drop me a WhatsApp on this number. It's specially for solving exam papers. When I go through questions from other students, then I'm going to also attend to your questions. Okay, but just make sure that you've watched this lesson 3 times. I'm thinking it's one of those lessons which confused me for the longest time until I mastered it. So now I'm confident with the graphs. Any type of a graph, I'm able to interpret it, and I hope you guys will understand my interpretation. Okay, so ladies and gentlemen, it helps to be ahead of your teacher, because when they teach you in class, you're going to have an idea as they explain these things to you guys. So it will make a perfect sense after you've watched this type of my lessons where I explain from beginner stage up until the last stage. So ladies and gentlemen, thanks very much for joining. My name is Desmond and I'm out.